Hello, my name is Walt Subkiel, and I'm going to be offering a presentation on systems engineering. Actually, this presentation was given at the Southern New Jersey Professional Societies, and this recording occurred a couple of weeks after that presentation. This all happened in February 2016. I'll try to highlight most of the themes that we hit that evening, but of course, obviously, the words are going to be different, and I'll probably have a few other different kinds of things to talk about, but hopefully there'll be, significant overlap between the two presentations. The content is system sources and definitions. I'll be talking about the books that I've generated, talk about the next generation, and then some book and course extracts. I have an area where I'll talk about some introductory material, human factors, technology, architecture and value systems, and sustainability. There is no grand story or theme. This is like basically picking up a book and selecting random pages and reading. And the best way to enjoy this little presentation here is to just sort of sit back and, take the content as it comes. It's going to be jumping around quite a bit, but just enjoy. Okay, system sources and definitions. This is an interesting topic. Whenever you get different folks together and they try to understand what systems engineering is about, the first thing they want to do is they want to sit down and have some kind of definition. They want, some kind of magic bullet answer. Where did this stuff come from? How is it defined? What are we really talking about? So let me just start off over here with system sources. And these are some references that a lot of people make, essentially. Most people will point to Bell Labs sometime around 1943 time frame in terms of systems engineering. Other folks will point to RCA with their experimental television system work in 1936. You of course have the British, where they were engaged in dealing with the whole situation there, the threat before World War II, and they basically had a multidisciplinary team to analyze their air defense system in 1937. Again, Systems Engineering Department was formed at Bell Labs in 1943. Bell Labs itself supported the Nike development between 1939 and 1945. Then I'll be talking about this thing called SAGE, Semi-Automatic Ground Environment. This was an air defense system, and it surfaced in 1951 and lasted till about 1980. And then there were previous or next generation systems that came after SAGE. And then 1956, systems analysis was something that was discussed and talked about by the Rand Corporation. Now, if we go take a look at some dictionary references, we'll see that there are some references going back as early as 1878, where there was a complete system of household and street sanitary engineering was surfaced and talked about, essentially. There is a railway system engineering reference that happened in 1916. And if we go to worldcat.org and we just take a look at the time frame between 1940 and 1950, and we search for keywords like systems engineering, you'll find 175 references. And then between 1950 and 1960, that number went up to 598 references. So continuing on with this whole definition and trying to understand where the word systems comes from, the earliest root of the word systems is systema, and that surfaced sometime around 1603. Some references say between 1610 to 1620, and essentially systema is a complex of anatomical structures that are functionally related. And this kind of makes sense because people were trying to understand how the human body was working basically at that time, and they were viewing that problem from a systems perspective. So what I want to do right now is I want to move into the modern era, and I want to talk about how other people define systems engineering today. And here we have an interesting definition. Systems engineering is a discipline that concentrates on the design and application of the whole, the system, as distinct from the parts. It involves looking at a problem in its entirety, taking into account all the facets and all the variables, and relating the social to the technical aspect. Let me reread that. Relating the social to the technical aspect. Now this surfaced from Simon Ramo, and Simon Ramo basically left Hughes Aircraft and founded TRW. So basically he was mentored by Howard Hughes. Very interesting, relating the social to the technical aspect. Continuing on today, if you look and get involved with systems engineering, you'll find out that there's an organization out there called International Council on Systems Engineering, and there's a handbook, and of course they try to offer a definition of systems engineering, and it tends to change through the years. But let me just read this thing over here. Interdisciplinary approach and means to enable the realization of successful systems. Okay, it focuses on defining customer needs and required functionality early in the development cycle, documenting requirements, and then proceeding with design synthesis and system validation while considering the complete problem, operations cost, schedule performance, training, support, test, manufacturing, and disposal. It considers both the business and the technical needs of all customers, with the goal of providing a quality product that meets the user needs. Interesting. So the second definition starts to list what is done when engaged in systems engineering, and it ignores the social aspects. I happen to prefer the first definition because a list of what to do is extensive and incomplete in the world of systems engineering, and it changes with time and the problem solution space. Also, the first definition is succinct. Okay, you're not reading off lists and lists and lists of items and your eyes roll back in your head. And more importantly is it works in all problem solution spaces, and the most important aspect is it includes the social aspects. That's what this is all about. Why else would we engage in any of these things unless we're trying to help ourselves essentially live a better life? Okay, so buried in all of this, eventually I came to the conclusion that there's why, what, and how. So to address this whole why, what, and how, I have this first book. It talks about why I think we need systems engineering. From my point of view, systems engineering is what we need to do in order to engage in sustainable development. I kind of go off the deep end over in that book, and I talk about it being the only answer for sustainable development. And then I have two textbooks that say, okay, we're going to do systems engineering. Well, what do we do and how do we do it? And the first one is called Systems Practices and Common Sense, and the second one is called Systems Engineering Design Renaissance, and there's others in the works. So, how did all of this start? Complicated story. It began with our little dog over here called Taffy. Taffy was with us in Florida. She came with us to New Jersey, and at some point I needed to write a short story about Taffy. And I discovered this thing called a Kindle on Amazon.com many years ago. And I wrote this short story about Taffy on the Kindle. But what happened was I got introduced to a new industry, which was the publishing industry, and displacement technology, which is publish on demand. And at the same time, I was interfacing with a colleague on sustainable development, and we were both engaged in systems engineering. And again, from my point of view, systems engineering is what we need to do in terms of enabling sustainable development going forward. And I had this story that I needed to basically write, and I wrote it literally within a week. It took about 40 hours to write it, and I wrote it on the Kindle. And again, I was learning about the publishing industry over there and what was going on with the displacement technology with Publish on Demand, and I decided to move this thing into the physical space. When I moved it into the physical space, I was essentially invited into academia. Systems Practices textbook. Basically, the idea here is to offer exposure to many systems practices, describe each of those practices, and then offer some examples. And I provide comments and opinions, there's homework, and there's core references. And I'm going to talk a little bit more about Taffy, what happened with Taffy, the publish on demand, the movement into academia, and why this textbook was written later on in the presentation. I think during the evening I probably jumped ahead and started talking about it at this point. So the issue is, which practices? What am I going to stick in this book? Well, these are practices typically found on large projects. They're new practices that are mentioned, okay? But research is actually encouraged to find new tools and practices. And the goal is to get the students/readers to modify existing practices or develop new practices to support their needs. What this book tries to do is give them a foundation, a core from which to build. So let's take a look at some of these practices. I'm just going to start to read these things off. Various introductory practices, that's kind of vanilla. We don't know what's inside of there. The process methodology, I'll talk about process there. Stakeholders and systems participants, system boundary, functions, performance, subsystems, operations and threads, human factors, flow charts, data flows, and structured analysis, IDEF0, state machine, interfaces and interactions, reliability, maintainability, availability, impact of failure. That's something new that I actually developed. Impact of failure, failure mode and effects analysis, fault tree analysis, fault tolerance, safety, security, modeling, simulation, prototypes, technology assessment and maturity. Few people address technology assessment and maturity when they talk about systems and systems engineering. In fact, few people hit all of these topics simultaneously when they talk about systems engineering. What they'll do is they'll maybe talk about requirements, maybe they'll talk about modeling or simulation a little bit, but that's about it. Continuing on, analysis and requirements, specifications and design artifacts. Let's keep going. Continuing on, architecture, concepts and synthesis, architecture and value systems, architecture selection and trade-offs, decision making. Are there practices? This is where I talk about, hey, we need to go out there and understand what's always going on out there that's new. Systems requirements database, integration test, verification and validation, configuration management, maintainability, training and education, integrated logistics and support, installation, decommissioning, disposal, quality, planning and tracking progress, earned value management system, major milestones and reviews, statement of work, procuring goods, services and systems, proposals and business plans, systems management, and then I end with sustainability and progress, because that's what all of this is all about. And again, most people, when they go and they start to address this whole space of systems, they'll talk about requirements, maybe they'll talk about modeling or simulation a little bit, maybe they'll talk about some kind of universal process and claim that there's some kind of systems process. Obviously, the space is very broad and very deep. This takes me into the next generation. So what happened? Basically, I wrote the little blue book, and I got invited to University of Pennsylvania. Essentially, I was there to help the senior systems engineering students in their systems engineering projects. And after the first year, I was working with the colleague that had invited me, and I said, you know what, we really need a textbook over here. Because here I am, I'm interacting with these brilliant kids. Oh my God, they're so smart. It's not even funny. My filament barely burns. You put me in a dark room, you'll barely see my little filament. These kids are so bright, you can't even look at them. But yet I find myself going up to the whiteboard and I start drawing pictures and laying things out, introducing them to the kinds of practices that I mentioned in this textbook that are foreign to them. They'd never seen them before. And yet I felt that they needed these kinds of tools under their belt in order to move forward with their projects. So after the first year, I concluded we kind of need a textbook. So the issue is, who's going to write this textbook? Coincidentally, Drexel University started to become interested in systems engineering, and they invited the Nkosi Delaware Valley chapter to help them understand this space. And the first meeting, obviously, there were a lot of people there that attended the meeting. We had our vice presidents, we had our directors, we had our senior managers there. And as time moved on, the vice presidents slowly started to go away, the directors started to go away, the senior managers started to go away, and we typically then wound up with working staff. And then eventually all the working staff went away, and I stayed. And at that point, Drexel opened up. and they started to essentially take me under their wing, and they started to talk to me about higher education, the challenges of higher education, and how it's different from industry. And they also started to ask fundamental questions. And one of the issues that I had is, why should I participate? Okay. And as I continued to attend these meetings, the questions that they were asking were very interesting and essentially very important. One of the questions they asked is, well, do we need to increase student enrollment? Well, the answer is no. Drexel always needs to turn away more students than it can handle. Next question is, well, if we're not going to use this to attract more students, why should we do this? Is there something here? And I will go into more details about this later on, but essentially they were coming from the education perspective and satisfying the next generation and what they thought was needed for the next generation. But I'm going to hit this more later on. Oh, here it is. Okay, so Drexel was starting to ask questions. I think the exact same thing happened during the presentation I gave live. The first question was, what do we mean by systems engineering? And I chimed in and I said, it's all about large complex systems engineering. Okay, why not use our current tenured faculty? I chimed in, I basically said this stuff was developed and selected for profits, nonprofits, federally funded research development centers, and government labs. And the kinds of things that the tenured faculty were studying really did not mix and did not happen within this kind of environment, within these kinds of settings, as these folks were trying to deal with the development and operations of large complex systems out there. Next question that they asked is there a body of knowledge here? And I said maybe, I really don't know. And we had several meetings on this, and after a while I just decided to show up with a 2-foot stack of paper, double-sided print. I think I picked like 8-point font, 9-point font. And of course the folks at the table, their eyes got wide and they got very excited, and they picked up the stack of paper. And about 30 days later, they came back. They said, you know what, we looked at this stuff. We kind of disseminated it through the organization, did some more research. And yeah, there really is a body of knowledge here. There's something going on here. And yeah, the tenured faculty has not addressed these particular areas. Next question it was, and this was very, very important, is this needed for the next generation? And I actually was saying yes. And it was coming from my little blue book. Systems engineering is the answer. We need to do this. And my perspective is that we have these complex systems, they surface, the genie's out of the bottle, and these complex systems can ruin everyone's day. And so, it's not 50 years ago, it's not 40 years ago, it's not 30 years ago. These systems were born that long ago. We're now moving forward, and this next generation needs something. So the next questions that were asked by Drexel were very, very important, and it kind of shook me to my core. Why should we do this? We created the engineers that developed systems engineering. What are we really talking about? And that was a tough and very valid question. And what I did is I actually tried to address that question in the introductions to my textbooks, and I also created an online video which captures essentially why I wrote these books, why they exist. And these videos and these words may have helped make the case, and obviously they went off and did their own due diligence, but they concluded, and this is really important, that this really is indeed needed for the next generation, and it doesn't matter how low the enrollments are. Even if the numbers of students are in the single digits, this is important. We need to figure this out for the next generation. Okay, so some extracts from the book and the course material. Introduction and Fundamentals. It was hard to try to figure out where to start this textbook. I chose to start it with what I consider to be the modern era of systems engineering, and I actually think that this was the beginning of what started to surface that became important. And unfortunately, it started with this terrible thing having to do with war, and specifically the nuclear bomb. When the nuclear bomb went off in World War II, we had the Manhattan Project, which did that, gave birth to it. The people, in my humble opinion, actually panicked. They really got scared. They knew that the genie was let out of the bottle, essentially, and there was no way to put it back in. And so what they did is they actually developed another program to try to deal with it, to try to somehow defend against nuclear war, as crazy as that sounds. And that program was called Semi-Automatic Ground Environment, SAGE. What happened was the whole idea of air defense and being able to get situational awareness, which actually started by the Germans during World War II. And these systems were analog based. You had radar sensors out there. They were looking at different things and feeding them to command centers where people were looking at what was going on, essentially on what we know of as radar scopes today. But those systems are one of the reasons why the Germans were able to basically roll over all those different countries during World War II. These systems, analog systems, because of the technology, they tended to be at a particular site. They had to be within, a certain size range or whatever, because you could not send the analog signals too far, and you were somewhat limited in terms of the amount of information that you could actually process. And what happened was an idea surfaced, and the idea had to do with taking all of the analog information, digitizing it, and moving it into a computer. Now, prior to that time frame, the computer was only viewed as a calculating machine. However, there were a group of folks over at MIT working on Project Whirlwind, and they were viewing the computer from a different point of view. They were trying to figure out how to use a computer in flight simulators as part of the Link simulation systems work and so on. And so the idea surfaced that, what if we digitized all of this information, fed it into computers, and the computers started to essentially process this information and offer it to operators. It would be like a TV display, but it really wouldn't be a TV display. There'd be map information there. There'd be alphanumeric information there. There'd be a keyboard there. There'd be essentially a trackball or a light pen. The British used trackballs. The Americans used light pens. But this was the birth of the semi-automatic ground environment. It's considered to be one of the most successful software systems out there. And on the left over here is a picture of the computer. This thing weighed 275 tons, had 55,000 vacuum tubes, and had 500,000 lines of assembly code. And what these folks had done is they essentially had these command centers, and they networked them around the world using telephone lines and other communications mechanisms. This is essentially the birth of our modern computer environment. The laptop that you're using right now, this is it, right here. The internet that you're using right now, this is it, right here. It all came from the semi-automatic ground environment, this thing where people tried to figure out if they could defend against nuclear attack. The other thing that surfaced was this idea of dual use, and somehow using funding to not only pay for defense but also have some benefit in terms of social aspects. That's getting back to that first definition from Simon Ramo. But that's really important, because what happened next is the interstate freeway system was born in this country. And in the United States, they've been trying to put roads in place since the early 1900s, and nobody wanted to pay for them. They didn't make economic sense from a business point of view. Obviously, the government wasn't going to pay for them, but because of this fear of nuclear war, the interstate freeway systems were born, and they were developed such that it could deal with what might happen in the event of war. For example, airplanes could land on these things. People could evacuate from cities, as stupid as that sounds. And again, the bottom line is no one wanted to pay for the interstate freeway system. And this was all done under this whole concept of dual use. And sustainability, right now we're talking about sustainability, and there have been a lot of changes that have happened, and we have these complicated systems in place right now that we take for granted. And the issue is, who's going to pay for these things, especially if they make no business sense at all, of course. Dual use has actually disappeared. It's no longer part of our vernacular. It's no longer part of our thought processes. It's a big issue. But this is how I start off systems engineering in my text and in my classwork. Okay, shifting gears over here, talk about a lot of different introductory material in the course and in the book. And this is just a random poll. I thought it was kind of important to maybe mention technology versus goal-driven systems. So in the text, I mentioned that there's 3 approaches to system development. One is to be mission goal-driven, the next is to be technology-driven, and the third is to be both mission and technology-driven. And then I say no approach is right or wrong. And, oh, by the way, different systems practices are used depending on what you're trying to do here, where you are. So, what does approach 1 look like, the mission-driven approach? You identify your goals, your mission, your needs, your requirements, and you create a system with current, modified, or new technologies, machines, and processes. And an example of this might be the setting of a goal of sending a man to the moon before the end of the decade. The second approach is technology-driven. In this particular case, you let the technology evolve on its own. People love this technology. They're just pushing it in some direction. They don't know if there's a use for it or not. They're just hog wild on taking this technology to its limits. So it's taking its own path of least resistance, and then someone says at some point, you know what, let's throw this into a real-world operational setting. And the humans proceed to then morph it into their world. An example of this is the internet. Nobody knows where the internet came from. Not in the society in general, all of the businesses out there. All of a sudden, internet technology appeared, and either people embraced it or rejected it early on. Now today we're completely wrapped around the internet and we can't visualize a world without the internet. But when this thing first surfaced, there were many people that rejected this whole internet thing. Again, those that embraced internet technologies have new systems that transformed their world. It changed everything. The third approach is goal and technology driven, and in my humble opinion, this is for extremely complex systems that must exist and work, and they're important to not rule out any possible avenues because these things are just so important. And the example that I use actually is a new air traffic control system with the need to increase capacity. That seems reasonable. That's a reasonable goal. And at the same time, new technologies are studied and tested to determine if they result in increased system capacity. So you have goals, missions, needs, requirements driven approach plus the technology driven approach, and hopefully the most effective system might emerge. Now, some people will say we should never use hope. Okay, we need to really have an understanding here. Hope is not going to get you to the end. You have to have a plan. You have to have some kind of strategy getting there. So this is a potential strategy. This presentation was actually given to an air traffic control audience, and in fact there's going to be lots of references to air traffic control in this presentation, and also in the textbook material and in the course material. Okay, shifting gears a little bit. Again, this is all introductory material. This whole idea of technology versus goal-driven systems. You know what? There will be a system, whether we like it or not. It's just going to be there. And the system can be great, and everyone just smiles and thinks, wow, what a great product, system, or solution. Or the system can be bad, and everyone is sad if they're forced to live with a bad system. So what do we do as systems practitioners? Obviously, there's an ideal system out there. You have effectiveness, right? And you're trying to reach the level of effectiveness where you have the ideal solution. And you have time, right? And then you have limitations. And your limitations are technology, politics, money, time, motivation, education, and people. And as time progresses, you remove those limitations. Now, in my humble opinion, in my world, I have no tolerance for anything except technology. Okay, this is grown up stuff. We cannot play games. The politics, the money, the motivation, the false time schedules, the lack of education, the issues with people, that all needs to be eliminated. Everything needs to be right, because what we're really dealing with here is technology. Okay, and hitting our limits, because we need to find those ideal system solutions. Continuing on with the systems practitioner's role, now, when we start off, we may not know what the ideal system is, and it takes us time to get there, to figure it out. And again, we want the ideal system because it's the most effective system. What can happen is we actually know what the ideal system is. We might know it instantly, maybe we find it along the way, but then our limitations start to kick in, and they start to kick in because of massive ignorance. And because of that ignorance, we move further and further away from that ideal solution. So we have different scenarios that can surface. And again, this is the role of people who are engaged in systems. We need to avoid these negative scenarios. Again, we have effectiveness. The dashed line represents where we want the system to be in terms of effectiveness. This is the most effective system we can do. Okay, and in the first graph, we're basically stuck. We just can't get there, whatever we do. In the second graph, up at the top, the middle up there, we have a sad story. We approached the effectiveness level of a system, and then we started to drop off. Something kicked in. Politics kicked in. Money kicked in. All of these negative things started to kick in. The third one is basically a criminal kind of activity. We know what the ideal system is out there. We even know how to do it, but you have all of these other limitations kicking in, and it's just criminal. You just move completely away from it. Continuing along, we have the graphs down at the bottom on the left-hand side. We have a miracle. We kind of knew what the effective system was. We started to move away from it as time progressed, and then a miracle happened, and things corrected themselves, and we started to move into the most effective solution possible out there. Then we have the no excuse solution. It's like, what's really going on there? Why aren't we able to do much of anything? There's just no excuse there. And then the last one, lower right-hand corner, that one is really critical. This is an arrogant team. They think they know what the most effective solution is out there, but in their arrogance, they're extremely ignorant, and they don't understand that what they're coming up with is not the most effective solution. In fact, it may actually be a bad solution. The arrogant teams are also teams that really, really bother me. And again, the systems practitioners, their roles are to deal with this. And ideally, everybody on the project, guess what? It's a grown-up world now. In my humble opinion, they all need to be systems practitioners. They all need to have that systems view. Okay, moving on, I want to talk a little bit about process, and I'm going to have an example here. I'm going to be talking about a process that's used to spur creativity and innovation. Now, this is a personal creativity and innovation process. I was exposed to this as a young man, actually, at a place called Cherry Hill High School West. And after I get through with this, I'm going to provide some academic references. It's basically a 5-step process. Step A is to saturate. You basically immerse yourself in the material, no matter how mundane or irrelevant it may seem in the beginning. You talk to everyone about the material and dialogue, if possible, with everyone. You incubate. What does that mean? Basically means you sleep on it and you let the miracle of the human mind go to work on the problem. Synthesis. This just happens after incubation. You can't stop it. It is human. Eventually approaches surface. You mature approaches as you continue to saturate and incubate. At some point, you're going to go off and start to optimize. That basically means you take each viable approach and move it to its most elegant limit. And then you have to select. It basically means you have to pick the approach. So if we go and take a look at this little process that I was introduced to as a young man in high school, it traces back to the 1800s. Herman basically introduced 3 stages to this idea of spurring creativity and innovation. He talked about saturation, incubation, and illumination. Graham Wallace, in his Art of Thought in 1926, introduced a fourth stage to the process. Basically, there was preparation, incubation, intimation, and illumination and verification. Again, all of these categories tend to follow what I just described. Now, you can take this personal creativity and innovation model and move it to the team, essentially. So a team saturates, a team engages in incubation, a team starts to synthesize, a team starts to optimize, and a team needs to select. So if you go off and you talk about these different events and you go from saturate to incubate to synthesis to optimize to selecting, those are all standalone events. And if you tie them together, essentially what you have is you have an event. There is no feedback between any steps. This is a series of events that just translates to an event. We don't have a process here yet. As soon as we start to introduce feedback loops, interesting things start to happen. At any time, we know that new insights might force the team to step back any number of steps. This is called feedback. And this starts to make it a process rather than a series of events. Now, the iteration rates very early on might be very quick. They might happen every 2 days, every week, every 2 weeks. In the later stages, the iterations might happen every 6 months, every 2 months. And towards the end of the stage of the system, or whatever we're working with, the iterations might be once a year, once every 2 years, or maybe once every 5 years. We still don't have a process, however. We have our events, so to speak. We have our feedback loops, but for us to have a process, we also need to identify the tools that we use for each of those activities that we're engaged in, and then we need to identify the artifacts, what falls out of all of these activities, what falls out of all of these events. So tools and artifacts and feedback are very important. So a process has key elements. It has steps, has feedback loops, has iterations, has tools, has artifacts. And a process is incomplete without any of these elements. Okay, I'm going to shift gears right now, talk about human factors. Human factors is a big topic for me. There's a lot of areas that are covered in the books. I'm just going to start to read them off, and then the course material. Vision and displays, hearing and audio, video audio compression, voice phraseology, touch tactile feedback, ergonomics, sensory cognitive data information overload, feedback, response time, vision versus sound, visual and audio noise, circadian sleep rest cycles, stress sources, HMI style guides and designs, and then ethics. Human factors basics. You know, in 1958, the people in the United States realized that they needed to do several things moving forward. And one of the things that they did is they established the Federal Aviation Act. And I'm just going to read this thing over here. The administrator shall undertake or supervise research to develop a better understanding of the relationship between human factors and aviation accidents, and between human factors and air safety, to enhance air traffic controller and mechanic and flight crew performance, to develop a human factor analysis of the hazards associated with new technologies to be used by air traffic controllers, mechanics, flight crews, and to identify innovative and effective corrective measures for human errors which adversely affect air safety. What does this mean? This means that the people decided to establish different kinds of research facilities, government labs, where people studied how humans interact with machines. They tried to understand what was going on with ourselves, with the way we see things, the way we hear things, how we're able to interact with different mechanical devices and so on, and gain a better appreciation so that we could have better systems. Now, this presentation was given to an audience of FAA folks, and actually these are the FAA folks chartered with this very execution of this law. Obviously, there's many different facilities around the country. This particular facility is called the FAA Technical Center. At one time it was called the National Aviation Facilities Experimental Center. And its purpose in life was to do just this, and it still continues. So I introduced the students and the readers basically to how our eyes operate. They're given a quick overview of our rods and cones, how they behave under different light conditions, monochromatic light, color light, and so on. So they have some view of the physics behind, again, how the eye works. And then they're shown a series of slides where they basically start to see what's going on in terms of the different light backgrounds, text backgrounds, and so on, and it's connected up with the science of understanding how the eye operates. So I'm just going to go through some of these slides very quickly. I start off here, something benign, blue with black text essentially. Okay, blue, white text, green text, black text, green background, white text. Oh, this is very interesting. This is where the eye starts to break down. Blue background, red text. It's amazing the amount of HMI interfaces that have been developed in the past 15 years, especially with the rise of the internet, where people are doing precisely this. They don't know how the eye operates. They don't take the time to even review what they've done to see if this makes sense for a user sitting in front of a computer terminal. Again, blue text and blue background and red text. I introduced them to what a blackboard used to look like. A blackboard with basically chalk on it. I tried to simulate it. Eventually we removed blackboards. We went to green boards. There's a reason why we went to green. It's discussed in the text. Okay. And color was introduced with the green boards. What were the optimal colors? There's a reason why we had orange chalk, red chalk, orange chalk, yellow chalk, green chalk. Okay. Here goes a blackboard with red text again. Continuing on, blackboard with blue text. Essentially blackboard with green text. And here we have essentially a computer screen where we try to optimize the different colors. Okay, we see orange, we see green, we see yellow, we see red. Essentially, we can read everything on the screen, and there's a reason for it. There's science behind this. Here goes our blue background, and all of a sudden we see that there's problems. So again, the students are shown these different colors, color backgrounds, color text. Again, they're told how the eye functions. They're also told that studies were done in labs to try to understand how the eye functions so that different kinds of standards could be developed. And there's a standard out there called MIL Standard 1472 that everyone knew about many years ago. But that's new information today. The new generation is completely unaware of MIL Standard 1472. They're completely unaware of these human factors studies. And this is so critical, so important, because every single piece of automation we work on today has display screens. Continuing on, color selection. Then I talk a little bit about contrast. Contrast is also a big issue. Transparent windows. Transparent windows were recently introduced. What does it mean if you have a transparent window on a mission critical system and something is being provided to an operator which is basically life threatening, and someone's life hangs in the balance based on what's being displayed, and there's a transparent window and you can't see it? Continuing on. They're told about the field of view that's available to their eyes, and what it means in terms of color vision, monochromatic vision. Again, this is all based on studies in these labs, science, understanding how we work. And we have basically field of view of eye rotation, field of view with head rotation, field of view with eye and head rotation. You put the things together. So we step away from one of the senses that we have, sensors or senses, in this particular case eyes, and we need to make sure that we can at least feed the information to one of our sensors properly, or senses properly, our eyes, and at some point we have to process this information. So we talk a little bit about human information processing and this idea of cognitive overload. And what does it mean if you're overloading the operator's ability to process all this information? This is a little diagram over here that tries to illustrate human information processing. We shift gears and we talk about circadian cycles. Such a big deal today. Basic things relative to circadian cycles and working out and developing a work schedule. We see that there are different work schedules over here. We have an 8-hour day, we have a 9-hour day, and we have a 12-hour day. And then we put the facts of life on there. People are driving to and from work. People need time for a break. They need time for lunch, and they need sleep time. And as we see, as we move from the 8-hour day to the 12-hour day, essentially all of the personal time is removed. When does the person get to decompress? When do they have the opportunity to deal with their own personal life? And there's a big issue over here because, for example, many people in the healthcare industry are all pulling 12-hour shifts. And I specifically used the example of my daughter, who's a physician's assistant in the emergency room. This is a mission-critical system. People are coming in there every day with life-threatening situations, and everybody's working 12-hour shifts or more. I can also talk about the surgeons who've operated on my wife on different occasions and how they brag about pulling 24 and 36-hour shifts. Okay, this is unethical behavior. We know this stuff. We have the science behind all of this. Okay, big systems issue. Circadian cycles and what are we doing to ourselves and what kind of systems are we really unfolding? Human factors. It's a big deal. Okay, then I shift off into technology, talk a little bit about technology. We're going to lighten up here a bit. Technology assessment and maturity. There's this idea of formal technology assessment, informal technology assessment. There's technology maturity and adoption, technology assessment and sustainability, prediction, function and performance allocation, misuse of technology. How do you actually infuse technology? There's different ways of doing it. And then what does this mean in terms of organizational longevity and this whole dirty word that no one wants to mention anymore called research and development. Again, I'm just going to cherry pick a few items out of that whole technology discussion that occurs in the text and in the classroom material. In this particular case, I'm going to introduce you to a thing called technology readiness level. The TRL is a gauge that identifies the state of art of a technology. And there are different TRL scales associated with different organizations. For example, NASA has a TRL scale. DoD has a TRL scale. The FAA has its own TRL scale. NATO has a technology readiness level scale. So does the European Space Agency. The good news is there is overlap between these different scales, and you can make sense of this stuff, and you can work across organizational boundaries. But you may have to do some translation as part of establishing a TRL scale for your particular activity, your particular organization that you're involved in at this moment. So the students are basically given some general descriptions of what the TRL scales are in terms of the different agencies. And over here I'm going to illustrate some of the key elements of the TRL scale. This is a TRL example. At level 1, there's basic principles that are observed and reported. At level 2, you essentially have a technology concept, maybe a proof of concept. At level 4, you have a laboratory environment. At level 5, it's beyond a generic kind of laboratory environment. It's starting to become very relevant to the current situation. You have a relevant environment, and you're dealing with components and so on. And at 6, you have a relevant environment, but now you're beyond the components. You're dealing with systems and subsystems. It's becoming more and more real. At level 7, you're essentially within an operational environment of some type. It may not be the operational environment that you're targeting, but there is some kind of operational environment that exists for this technology. At 8, essentially this thing is qualified through test and demonstration. Okay, and at 9, there are successful mission operations that are specific to your specific need, to your specific project, your specific system. So this is an example of a TRL scale. The students and readers are then introduced to this whole idea of technology maturity. There's this thing out there called the logistics curve and diffusion of innovations. And basically what we see is we have innovators coming in very early. We have early adopters. We have an early majority. We have a late majority. And then we have laggards. And we have some percentages of folks that tend to get involved in each of these categories of technology maturity. And we see essentially a market share that exists as this thing becomes older and older and then eventually becomes obsolete. And what you can do is you can take this information and you can sit down and you can start to assess an organization. You can take a look at that organization, pick all the different business areas. In this particular case, we have 2 business areas. Each of those business areas are engaged in producing some kind of product. To produce that product or system, they're using some kind of process. They're using some kind of tools, and that product or that system itself is at a particular level in terms of technology maturity. So we can have, for example, let's look at the last 2 lines over here. We can have a product that's state of the art. It's using obsolete tools and a dated process. And you now can step back and say, wow, does that really make sense? What are we really doing over here? We can also take a look and say, you know what, we have a system or a product here. It's dated. That's a kind way of saying the thing is obsolete. But yet it's using leading edge tools and bleeding edge processes. Again, does this make any sense? So some bullets takeaway down here. The organization can be evaluated for technology maturity. You can think in terms of processes, tools, the product line, or system. And with all of this, you can visualize the remaining market share and compare it with the marketing folks and what they claim is the market share out there, which is amazing because typically marketing folks will come in and say there's a huge market out there, and essentially you're dealing with dead technology. You're dealing with a dead product. There's nothing left out there. Okay. At some point, product line or system needs technology infusion for it to become viable again. Okay, we're shifting gears. We're going to move into architecture. Today, when many talk about architecture in the systems engineering space, they immediately start to refer to a thing called DODAF or MODAF. Some of them will go back to TAFM, and obviously they're talking about computer architecture in those particular cases. What I do is I actually take the readers and the students back to a couple of thousand years ago, basically. I talk about the 10 books on architecture from Marcus Vitruvius, surfaced about 15 BC. And some information is provided to them. And then I move them very quickly into the 19th century, where I talk about Louis Sullivan, who basically came up with concepts of form follows function. In other words, a building or object shape should be based on function or purpose. And then I move them quickly into the last century with computer introduction, where the computer itself embodied an architecture, and its introduction transformed the architecture of organizations. And the results could be good or bad. So the architecture discussion, is very, very broad. I go back a long period of time and again move the students forward. Now, architecture, in my humble opinion, is about 3 very important things. There's this idea of alternatives, depiction, how are you going to show the architectures, and then selection. So here's a little diagram where I talk a little bit about architecture synthesis, and what we have here is we sort of have a process going on, and we see that we have events over here and so on. And step A is we identify our real needs, and basically we have customers and stakeholders that participate in that particular case. We surface our key requirements. In this particular case, we study the past, present, and future, and we innovate. We identify alternative architectures. Again, we study the past, present, future, and innovate. And then we optimize our architectures. And the way we optimize our architectures is through our studies, our engineering studies, our science studies. Even our soft sciences studies are extremely important in these areas. And then we select our final architecture using this thing called measure of effectiveness or trade-off. So synthesis is aggregation, putting things together, and it's the opposite of decomposition. It's reverse decomposition, take known and generalize until details are removed. That's one of the approaches you can follow. And it's done in an environment of analysis, models, alternative architectures, technology assessment, failure analysis, etc. Then I introduced this whole idea of architecture and value systems. At some point, an architecture needs to be selected, and that selection is extremely important. Architecture analysis is used in this selection. Basically, you have front-end systems practices. All of this stuff should be immune to external influences, right? You can't have anything compromised going on over here. And the evidence needs to be traceable to formal and informal studies. And the selection is based on the concept of value. Which architecture has the greatest value is a fundamental question. Now, we have different ways of measuring things in terms of value. There's financial metrics and value. So for example, we have lowest cost, highest cost, greatest return on investment, total cost of ownership, internal rate of return, economic value added, real option value, return on assets, and then return on infrastructure employed. And unfortunately, many government agencies, for example, like this ATC FAA audience, is stuck with return on infrastructure employed. Decisions must be made, and the decisions are based on values. However, most approach this from a financial point of view. But value is more than financial. For example, some value a day at the beach more than a day at the mountains. And this can be captured with this thing called the measure of effectiveness. And the measure of effectiveness is essentially the sum of trade-off criteria divided by the total cost. So if you could visualize, you have different criteria that you've surfaced as part of your architecture analysis. They essentially form rows in the matrix. And then you have columns that represent the different alternatives. And somehow you're rating these trade-off criteria, and then these different alternatives have different total costs. Your life cycle costs essentially represent these costs. And the life cycle cost, this is easier said than done because, for example, there are indirect costs or infrastructure costs which a lot of people will push off to other stakeholders in an unsuspecting fashion. Okay, and then you have environment and waste. So this whole issue of truly identifying the cost of a system, of an architecture, is a very tricky proposition. I mean, we know about research, development, production, operations, maintenance, and some of us also know about shutdown and disposal. But this whole idea, again, of indirect costs and infrastructure costs, and what is your architecture really doing to the rest of the systems out there, and these are new ideas that are surfacing, and we're learning things the hard way, that this is a very difficult situation. Then, of course, environment and waste. So what can we do? Architecture selection and trade-offs. What we can do is we can identify our architecture alternatives. We can list the advantages and disadvantages of each approach. And then we identify trade-off criteria. And we can use the list above as a guide to try to surface some of these trade-off criteria. We create a trade-off matrix with trade-off criteria and alternatives. And then using science and engineering, we fill in that matrix with some kind of value for each cell. We determine the life cycle cost of each approach, and then we divide the total rating of each approach by the life cycle cost. Again, this is the measure of effectiveness of each approach. It's a measure of goodness for each dollar spent for each approach. So pictorially, this is what it looks like. We have our trade-off matrix at the bottom. We have our advantages, disadvantages list up at the top. We have our criteria 1 through N. And again, the tricky part is filling in those numbers, and that's all based on analysis. We have to be really careful that we don't compromise ourselves in this particular area. We have to do the analysis, and we have to do our best to somehow rank these different alternatives in this matrix. So the measure of effectiveness, keep going back to it. It's the sum of the trade-off criteria divided by the cost to produce each approach. Now the MOE equation is the heart of systems engineering, in my humble opinion. That's it. It's fundamental. It's like F equals MA in physics. It drives everything. Your trade-off criteria ratings are the results of analysis, and the analysis is based on engineering and science. And you do this like your life depends on it, because you know what? Maybe it does. Okay, this takes us into sustainability. Again, in the text, in the course material, I talk about the traditional definition. Most people offer the Brundtland Commission's definition of sustainability. Essentially meets the needs of the present without compromising the ability of future generations to meet their own needs. What I've done is I've actually taken this whole issue of sustainability and broken it into two. There's this concept of internal sustainability and external sustainability. Internal sustainability is the ability of a system to sustain itself. We have roads, we have water, we have sewage, we have housing, we have transportation systems, we have communication systems, we have education systems, we have trains, we have planes. We have to be really careful because this stuff can wink out. And what are we going to do if it winks out? It took years to put these systems in place. Okay, so there's this whole idea of a system being able to sustain itself, internal sustainability. Now, external sustainability is what most people view as sustainability. This is essentially the system impact on its surrounding community. Now here's the bugaboo, here's the challenge. Internal and external sustainability, they both have to be addressed. We cannot do one without the other. We cannot have whole systems wink out of existence because we need them moving forward. And at the same time, we cannot have these systems impacting other systems in such a way so that the entire world gets ruined. Very, very tough challenge. Internal sustainability, external sustainability. So I've taken the V diagram that we see in many different systems engineering settings. Sometimes it's shown in terms of process, sometimes it's shown in terms of test. In this particular case, what I've done is I've augmented the V diagram, which tends to be more process oriented over here, and I've added what we should consider when we talk about sustainability. I introduced the concept of some kind of community sustainability document report, and this community sustainability document report is developed very early on during the concept definition, prior to the concept definition of the system. And as the system moves from concept of operation, system requirements, subsystem requirements, component requirements, implementation, then we have our unit verification, subsystem verification, system verifications, and system validation and delivery, where we are basically designing and recombining all of this stuff. At some point, this stuff goes operational. A lot of people tend to wash their hands after system validation. System operations, that's someone else's problem. Excuse me. And then after systems operations, eventually these systems get old. They need to be decommissioned in someone's eventually, and someone has to deal with this whole issue of decommissioning. Someone else's problem. Excuse me. No, we need to think about these things when we're developing these systems initially. So we see community sustainability on the left. We see shutdown disposal and operations on the right. We don't wash our hands with delivery, just throw it over the fence and run away from it is the best way to describe it. Then I take the students back into this whole idea of dual use that existed when all of this stuff started. And there are several public laws that surfaced that are so fundamental, so key. They drove so much of what happened in the past 50, 60 years. I mentioned the Federal Highway Act of 1956, which gave birth to our interstate freeway systems. We would not have a modern society today without those freeways. There'd be less people that could actually live today without these freeway systems. Who gets to decide who lives and who goes? The NASA Space Act of 1958. Amazing piece of technology surfaced from there. We take all this stuff for granted. This was not an easy thing to do. Enormous amount of work. Hundreds of thousands of people working across the planet, if not millions. Very, very key. And then even the Federal Aviation Act of 1958, we take for granted our travel, our airline travel, our airplane travel that we have today. But this whole idea of actually studying how people interact with a complicated system like airplanes and air traffic control systems, was embodied in the Federal Aviation Act of 1958. Very, very important ideas. Okay, so the final takeaway. Final takeaway, most people say, I know the process, I know what is expected, but I don't know what to do. Okay. It is about selecting the appropriate practices and then executing those practices. That's the position I'm coming from, and that's what I'm hoping these texts have done and what these course material has done. So Book 1 and Course 1 attempts to describe and show how to execute many practices used in complex systems engineering settings. Now, there's other topics. There's design, there's architecture, and software, but those are other presentations for another day. Thank you. Now, the book itself has 142 references. It's a little over 700 pages, and I go back to some of the fundamentals in terms of government standards that were developed when all of these systems were being born. There's just enormous amounts of information in those standards, and unfortunately the new generation is not aware of these standards. The early standards actually captured some of the kinds of thoughts that people had in terms of how do you go about doing these things. So there's incredible information in there. The book references these standards, these guidelines, and so on. And I just wanted to provide an overview of this, and I also wanted to mention that there's a huge body of work that actually has been documented, and it does exist out there. But it is winking out. It is slowly disappearing. Some companies are actually claiming ownership of this stuff, and it's becoming harder and harder to find this, even though it's all in the public domain. It was all paid for by the taxpayer, and we all have access to it.